We're going to talk about various special cases of vector fields on the plane, namely those vector fields who come from gradients of scalar valued functions. In other words, if you are given a function fxy, a real valued function on the plane, you can take gradient and at every point it gives you a vector, namely the vector of partial derivatives, which I have written in different ways here. Now, among generic vector fields, these must be special. Something should be unique about these vectors, and we're trying to understand that. And for a generic vector field in the plane, of course, we have I plus j, where I and j coordinates are real valued functions of x and y in turn. Let me point out a first observation about this. So we see that in the case that gradient of f is pi plus qj, partial of p with respect to y is, well, p happens to be f of x. That will be partial of partial y of f of x, and that is fxy. On the other hand, partial q over partial x is partial x of q here is partial f partial y, and that becomes fyx. And remember that for continuously differentiable functions, these are equal. And we always assume such conditions on functions. So we see that partial p partial y equals partial q partial x. So of course, for a generic vector field, there is no reason for there to be any sort of connection between p and q. P and q are not even talking to each other. Therefore, this property is unique to those vector fields that come this way. We will talk about the reverse as well. So what we showed here is that, so the first important fact is that if a vector field pi plus qj comes from gradient of some other f, then we must have partial of p partial of y equal partial of q over partial of x. The reverse direction, we have to wait a little bit. So this does very emphatic not mean that if we do have this condition star, then necessarily a vector field is gradient of f for some f. So we will see under what condition this will be actually true, but there are some domains on which this is not the case. So that is the first restriction. If a vector field is to be of the form gradient of f, these are called gradient vector fields, we must have this condition on partials of p and q. But let me backtrack. This comes a bit later in that section if you're reading the book. Another important fact about gradient fields. So if C is a curve from point A in the plane to, maybe let me use just P, point P to point Q, and f is gradient of f for some f of x, scalar valued, then this is a consequence of the fundamental theorem of calculus. It is also called the fundamental theorem of line integrals, although I don't think it deserves that name. It's simply fundamental theorem of calculus. Instead of doing it on a line segment, we're doing it on a bent segment. So what it says is that integrating this function, this vector field along the curve dr, of course this is topic of 16.2 where we did define these creatures. This happens to be equal to evaluated f at q minus evaluate f at p. So f is scalar valued function, therefore the end result will be a number, as it should be, because this is one number. So this is very important fact, again unique to those vector fields that come from gradient, that says to find the integral along a path, simply plug the endpoints into f and subtract. So let me draw a picture. So here is P, here is the curve C, parameterize. It doesn't even matter how you parameterize it. That says it only looks at the end values and subtracts, that becomes it. This is fundamental theorem of calculus and analog, because what it says that if you integrate f prime of x dx from a to b, you only plug b into a and a into a and you subtract. That's fundamental theorem of calculus, and you see the analogy here. The analogy being that you integrate in the derivative, so f is derivative of the scalar f. And there you go. A consequence, an observation from this is that integral depends only on endpoints and not on the specific curve. We had seen before that this integral, in general, integral of any vector field is independent of reparameterization, but this is saying much more. It says take a completely different curve that joins them. You can, of course, if you have a choice, you always take the simpler line segment, but this says no matter how, even if your curve self-intersects and ends here, integrating along the curve will produce the same value. And this property is singled out. So for a generic vector field, pi plus qj, not, that means when I say generic, that means not necessarily a gradient type. It is of interest to know if integral of that f, so let's call this big F, dr, is independent of path. Here's some fact again. This one we can find an easy proof of. For a vector field, f, not of gradient type, the integral, the path integrals are independent of path and only dependent on the endpoints if and only if integral of f over curves that are closed is always 0. So if this is 0 for all closed curves, that means if you have a loop, you start at P and you have a curve that comes back to it, P equal Q, then you need to have integral of f over this dr is 0. So let's see why these are equivalent conditions. It says that to test whether integral along path is independent of particular path that you take, you only need to check for closed curves. So what we can do here, you take any point in somewhere along the path. This integral from here, so let's call this point maybe z, and we can look at these two integrals. Call this c1 and call this c2. If the path were independent of depended only on the endpoints, we would have that this is equal to integral of c2, and orientation matters, so my points are both going from P to Q, so this would be f dot dr, and then that means integral of negative c2, that would be going backward, of f dot dr, negative c2, plus c1 f dr, which would be 0 because this one is negative of integral c2 of f dr, and this is by this equality equal to c1 of f dr, so they cancel each other. But notice that this side together, these two added together, fixes the orientation. That means we are following the red loop, which is the original curve, closed curve that we had. So this shows that if independent of path, that means here, if we have this assumption, then we have that for closed curves it's 0. And now let's go backwards. Suppose that we know that for every closed curve we have 0. So what happens then is we want to show that path integral is independent of the path and only depends on the endpoints. So you take P and Q, you take C1 and C2. Your goal is to show that integral along C1 is the same as integral along C2, assuming that for closed curves we have 0. So what happens? C1 f dr plus minus C2. So let me actually put it first here. Minus C2 integral f dr. Our goal is to show this is 0, but this is equal to C1 union minus C2. So reverse the orientation of one of them. And now I'm looking at this closed loop. So it is now a closed loop, and I have assumed that for closed curves I have 0. Therefore this becomes 0, and it implies that integral along C1 is the same as integral along C2. Okay, so what we concluded again is that path integrals of a vector field are independent of path. Let's avoid this repetition. Integrals of f along curves are independent of path if and only if integrals over closed loops, integrals of f over closed loops are 0. So we have seen that if f is a gradient field, then this property holds. This property holds also that if f is pi plus qj is a gradient field, then partial of p over partial y is equal to partial of q over partial x. So two properties for gradient fields, or maybe three if we include these as separate properties. So if you are a gradient field, let me write a much better sentence, okay? I love bullet points, as you may have guessed, and let me do it this way. If this is gradient f is, if we have a gradient vector field and we write it as pi plus qj, then three properties hold. First of all, integral c f dr only depends on endpoints. Two, integral of f c dr is 0 for all closed curves. And three, partial of p with respect to y equals partial of q with respect to x. So these three properties are true for vector fields that are of this form. Notice how many times I repeated this phrase that a vector field is of this form, a vector field is of this form. That's why they have given this a name. Definition, we say f, which can always be written this way, is a conservative vector field if it is of the form gradient of some scalar function for some f. Yep, so that's a definition among us. So next time I say some vector field is conservative, I mean this. So we can add this definition here. So i.e. f is conservative, then. Now a big question is the converse. If you give me some vector field, if you write a vector field at random for me, so 2x I plus x squared minus yj, can I know whether this is gradient of some scalar valued function? Can I write some f of x y equals, say, maybe x squared minus y squared or something, so that when I take gradient I end up with this? When is this possible? How do we tell it, both geometrically and algebraically? That will be the question of our next lecture. Very important question with deep connections to topology, in fact, and much deeper notions in geometry, which we won't get into. We will just provide an answer in the simplest form. Until then, have a good one.